Hello everyone, myself Yogita Mahatekar. In this lecture, we are going to see what is normal distribution, its probability density function, and how to calculate probabilities using the normal distributions. I am sharing my screen. So let us first of all go to RStudio. In help, in files and plot window, we can take help, visualize the commands which are based on normal distribution. So suppose simply I type normal distribution in files and plot window, we will get the information corresponding to the distribution. So here we can see what is meant by a normal distribution, what is binomial, and so on and so forth. There are 4 basic commands. So if I click on normal distribution, it will give you everything that is related with this distribution. So the density function, distribution function, what is meant by a quantile function, what is meant by a random generation, or the normal distribution with mean which is equal to mean and standard deviation equal to SD. Everything is getting displayed in this help window. So density function is the probability density function corresponding to a normal distribution. So let us first of all see what is the probability density function for the normal distribution. So probability density function of a normal distribution is denoted by this notation fx mu sigma square. X is the value of a random variable which follows the normal distribution, namely this probability density function. Mu is the mean. Sigma square represents the variance, which is always positive. Mu lies in between minus infinity to infinity, and its probability density function PDF is defined by 1 upon square root of 2 pi into sigma e raised to minus x minus mu whole square upon 2 sigma square, where x lies in between minus infinity to infinity. So the random variable is said to follow a normal distribution with the parameters mu and sigma square if its probability density function is given by this small f of x, which is defined over here in terms of exponential functions. Now one might be interested in how this small f of x will behave. So we can plot this function small f of x for all real numbers small x corresponding to these densities. So on horizontal line, we will take any real value or the interval, a finite interval, which is a subset of a real line, and on y-axis we'll plot corresponding densities. So it will follow a very interesting curve which is also called as a bell-shaped curve. The maximum value of the small f of x will be at mu, and the variance is equal to sigma square. So let us see how this probability density function we can plot in R software. So let me switch to R. So in this R software, we will come to a console window. So there are 4 windows. So in a script window, I have written few commands. So let me just maximize script window slightly. Now here one can see commenting I have done with hashtag. So if I take this command that I have written already over here, so let me just highlight that. I'm talking about this command. Curve inside a round bracket dnorm. Dnorm is a first function that is related with a normal distribution. So dnorm command that we can see in this help and help command, or using help command we can see what this dnorm function will do. So this dnorm command will find out the density for that value of small x, whatever is your mean. So suppose we are using a standard normal random variable, standard normal random variable will follow a normal distribution with mean is equal to 0 and standard deviation is equal to 1. So this D stands for the density. So it will give you probability for that value of x for the normal distribution with mean 0 and standard deviation 1. So if your mean and standard deviation values are different, you can insert it over here. Suppose you are not going to give any value for mean and standard deviation in denorm syntax or even in any other command, we are going to see these commands later, then it will take mean 0 and standard deviation 1 by default. So if you are not going to provide any value of mean and standard deviation in the syntaxes of all these 4 commands, then our software will by default assume it as a standard normal random variable and will take mean 0 and standard deviation 1. So let me just first of all copy this first command curve. Denorm means densities we will plot for the various values of x. Okay, so I have to give the x ranges. So x ranges I have given here from -5 to 5. C stands for the creation of vectors in R software. Y-lab means that you are labeling your y-axis. So your y-axis is labeled with respect to the phrase, namely a normal distribution, and the main title of this particular graph is a normal density function. So main stands for the main title of the graph. So normal density function is the main title of the graph. So let me just copy this command that I have written in the script file and let me just take it over the console. So I will paste that command in the console. So one can see this command is appearing in the console. So you can try it out on your own. To compile this, I will press Ctrl Enter by clicking on that particular command at the end. So Ctrl plus Enter if I do, you can see a normal density function is displayed in the files and plot window. Suppose if I zoom it, you will get this kind of bell-shaped curve. From -5 to 5, it is going to appear because we have given x limits from -5 to 5. It will take maximum at the mean 0. So we have given mean value to be equal to 0 and standard deviation it is assumed to be equal to 1. Normal density was the labeling of y-axis that is appearing along with y-axis. So max to max your probabilities are going below, slightly below 0.4. So this is how we can plot the corresponding density function. So suppose if I say I have to change the mean and standard deviation, I can do like that also. So if I go to again a console and if I change mean and standard deviation to be equal to say 3 and 7.2 say, and if I again do it, then you can see the maximum is appearing at that mean which was equal to 3. So the maximum value that bell-shaped curve will take is at x is equal to 3, which is namely a mean. So at mean you will get a mode, whatever is your mean value at that time, at that particular time parameter, or you can say at that time, at that particular independent variable x, its value, the function will have its maximum value. Now we will solve examples using these commands. So the denorm command will stand for the densities corresponding to your normal random variables x, taking value from -5 to 5, and we have plotted corresponding densities and we are getting a bell-shaped curves. So denorm command will give you the corresponding densities, or you can say the probabilities at a particular value x. Okay, now let us solve the example based on normal distribution. So let me just open the example window. So I hope this example is visible. Now in this example, what we are going to do is we'll solve these normal distribution example with the help of R commands. So let me go through the example. A research scientist reports that mice will live an average of 40 months when their diets are sharply restricted and they are enriched with vitamins and proteins. Assuming that the lifetime of such mice are normally distributed with a standard deviation 6.3 months, you have to find the probabilities that the given mice will live more than 32 months. That is first question. Second question is less than 28 months, and third question is more than 37 months and less than 49 months. Answers are also given for all those three parts. So basically, first we need to understand is here the random variable capital X is the lifetime of the mice, which is a continuous random variable. And also it is given that the lifetime of such mice are normally distributed. So when normal distribution comes, it comes with the two parameters, namely the average or mean, which is given to 40 months. So mu is equal to say 40. So mu stands for the mean of this normal distribution, which is equal to 40 months, and the standard deviation will denote it by sigma. So that I will call it as SD, and that is 6.3 months. So with this mean and standard deviation, we need to find out the probabilities. Probability, A part of the question. We have to find the probability that the mice will live more than 32 months. So how will you express in terms of probability statement? It will be a probability, P stands for probability, that your lifetime capital X is greater than 32 months. So you know mean and standard deviation is also in unit, namely month. So the probability statement will write in the same unit. So capital X greater than 32, its probability we have to find it out. So let us go to R console, and then I will tell you how to find this probability that capital X is greater than 32. So let me again go to help command. Now here we have already displayed all those four commands. So we have seen the use of dnorm command to plot the density function. Now pnorm, the second command, that is pnorm, is having a syntax. Inside a round bracket, you have to say that q comma mean is equal to 0. Whatever is your mean and standard deviation, you give it, otherwise it will be 0 and 1 by default. Lower tail true means you are finding probability for capital X less than or equal to X. So let me just go to again that example. So basically the A part of the question says that I have to find the probability that X is greater than 32. So namely, we have to find out uh, probability X greater than 32, say. So this we can do using pnorm command. Now I will tell you what is the use, how to use this pnorm command while finding these kind of probabilities. So first of all, this pnorm command, what it gives you, it gives the probability that capital X is less than or equal to small x. So it will give you the probabilities for lower of your capital X. So when your capital X lies less than or equal to small x, then we call it as the lower tail. So how is the syntax of this pnorm command? This pnorm command is having the syntax that you first of all give you that value x, or in the help window they are calling it as q, say. So say for example, suppose I call this even as some constant, say, and you have to find out the probability that capital X is less than or equal to q. What we will do, we will write like this, and then this pnorm command, your first parameter will be q, comma whatever is your mean. Your mean is 40 months, I will write mean is equal to 40, and standard deviation SD is equal to 6.3. Now here if you write these kind of command, it will give you the correct answer. Or you can also do pnorm. uh, So basically this P norm Q mean is equal to 40 and SD is equal to 6.3 is probability that capital X is less equal 32 or strictly less than 32. If a single point in the continuous random variable is not going to make any difference in the probabilities, because the probability at that single point 32 is almost 0. So this will give you probability that X less than 32. But we want a probability that X is greater than 32. So I will do 1 minus P norm of this Q. So right now what is Q? Q is taking value 32. So it will be 1 minus probability. So it will be 1 minus P norm of 32, mean is equal to 40, and standard deviation is equal to 6.3. Because when I do 1 minus p norm of this, it will be the probability that X is greater than 32, which is a complement of this first part. So p norm command will find out these probabilities for lower tails, but I want the probability for upper tail. So you have to take the complement of this event. So it will be 1 minus p norm of that lower tail. So let us see actually how we can do it in this software. So here I have written already that particular command. So in the mice example, to find the probability that mice will have their life greater than 32 months, what we can do is we will just um write down p norm 1 minus p norm 32 comma 40 comma 6.3. So let me just copy and paste it in console. So if you just copy this command and I will go to console and I will paste it, and suppose I have to run it, I will press Ctrl plus enter. It will give you the answer 0.8979294. So this is the probability that the mice will live their life greater than 32 months. And I hope this answer is my answer whatever is given in the sheet. Okay, so let me just go to there. So here you can see the answer is also given. The answer is 962 something. This is by using statistical tables we have found it out, but using software you will get a more accurate answer. Similarly, you can solve the B part. B part is what is the probability that the mice will live less than 28 months. So less than 28 means we have to find the probability for lower tail. Lower tail is true, you also you can say. So you can again use p norm command. So it will be a p norm 28 comma 40 comma 6.3. The one important feature of R software use you can understand is there is no need to convert this usual normal distribution or a random variable to a standard normal derivative or standard normal variable, say capital Z. Now secondly, that command also I have written over here in the script files to find the probability that the mice will live less than 28 months. So suppose we have to find out the probability that mice will live less than 28 months. What we have to do is you have to find out p norm of 28, 40, 6.3. Let me test that over here in console. So if I control and enter this particular statement, it will give the probability 0.028. So the probability is very less. So that answer might be present over here. So that answer is matching. C part is so you have to find the probability that the mice will live more than 37 months and less than 49 months. So in other words, I have to find the probability that 37 is less than capital X is less than 49. We can write this statement as probability that capital X is less than 49 minus the probability that capital X is less than 37. So here, before I go for the solving of third part of this question, I can show you the equivalent commands for finding the probability that mice will live less than 28 months. So this part we have seen. Equivalently, we can say that p norm 2846.3 for which lower tail is true. If you say lower tail is false, it will give you the probability that capital X is greater than 28 or greater than or equal to 28. Equivalently, we can convert this capital X in terms of capital Z stands for standard normal random variable. So how will we find out the standard normal random variable corresponding to 28? So we will do x minus mu by sigma. So it will be 28 minus 40 by sigma, which is 6.3, which is equal to minus 28 minus 40 is minus 12 divided by 6.3, which is equal to minus 1.9. And when I apply p norm of minus 1.9, it will give you the same answer. So let me just compile last two commands. So here I am saying lower tail is true. It's an equivalence that lower tail is true means capital X is less than or equal to 28. When I press Ctrl plus Enter, you can see the previous answer and this answer is matching. Even if you don't say anything with respect to lower tail true or false, it will give you the same answer. It will assume by default that lower tail is true. So we have to take care when you have to find out the probability for upper tail. And equivalently, we have found the Z value for 28, and for lower tail we'll apply p norm command. So if I compile this command in a console, one can see again the answer is same. So here when I just say p of minus 1.9, the R software is assuming that your mean is 0 and standard deviation is 1 by default. Now let's go towards the third part of the question. They were asked to find out the probability that the mice will live their life in between 37 more than 37 months and less than 49 months, which we can write it as probability that 37 is less than capital X is less than 49, which is probability that X is less than 49 minus probability that X is less than 37. So it will be P norm of 49, 46.3 minus P norm of 37, 40 and 6.3. So if I compile this command in console, we will get the answer 0.6464669. So that we can always see in the answer also. This answer will slightly differ because this is calculated using statistical tables and not using the software. Software will give you more accurate answers up to so many decimal places. Now let us solve the second example using R. Let me go through the example first. A lawyer commutes daily from his suburban home to his midtown office. The average time for a one-way trip is 24 months with a standard deviation of 3.8 minutes. So mu is equal to 24 minutes and standard deviation sigma is 3.8. Assuming that the distribution of trip times is normally distributed, it means that your capital X is trip times, which is a continuous random variable. First, A part, we have to find the probability that the trip will take at least half an hour. Now here if it says at least half an hour, it will say, suppose I convert it in terms of minutes. I can write this A part of the question like probability is that capital X is greater than or equal to 30. So while using pnorm command, we have to convert first of all this first statement of probability in terms of 1 minus probability that capital X is less than 30. So let's go to our console. So in this lawyer example, we have to find the probability that the trip time will take at least half an hour. So we have to apply this command 1 minus p norm of 30 mean is equal to 24 and standard deviation is equal to 3.8. So let me copy and paste this command in the console. And if I run this particular command, give me the answer 0.0571 something probability that the trip time will take at least half an hour. So this is such an easy technique without converting capital X in terms of standard normal random variable. Directly by using commands and complementing of events, we can find out the probabilities. Second question is the B part of the question. If the office opens at 9 a.m. and if he leaves his house at 8:45 a.m. daily, what percentage of time he will be late for the work? So he is leaving at 8:45 and office opens at 9. So if this if his trip time is exceeding 15 minutes, he will be late for the work, isn't it? So if trip times is greater than 15 minutes, he will be late for the work. So we'll find this probability first using R and then we'll multiply by 100. So that will be the percentage of time for which he will be late for the work. So that will be the answer for B part. So let us go to R. So equivalent form I will not show. I will go to the statement to find the length of time. Sorry, I think second part I have not solved because it's quite same, but I will show it over here in the console. So probability that X is greater than 15, we can write as P1 minus P naught of 24 is the mean and 3.8 is the standard deviation. So this will be the probability that he will be late for the work. So let me press Control Enter. So 0.9910 is the answer for the probability. So in other words, 99.10679% of times the lawyer will be late for the work in this case. If he leaves at 8:45 and reaches, and if office opens at 9 a.m. Now the B part, C and D part, basically C part is saying or asking us that if he leaves house at 8:35 and coffee is served at office at 8:50 a.m. until 9 a.m., what is the probability that he misses coffee? So if he leaves at 8:35 and the coffee is available till 9, if his trip time is exceeding 25 minutes, he will not get the coffee. C part of the question statement you can write like probability that capital X is greater than 25 we want. So as we have solved B part of this question, you can similarly solve C part of the question by changing accordingly your parameter from 15 to 25. And you will get the answer of that probability that he will miss the coffee. Let's go to D part of the question, which is slightly important because it will introduce us to use the different kind of command, namely qnorm command. Now in D part, find the length of time above which we have to we find the slowest 15% of the trips. So in other words, we have to find the probability that we have to find the small x value, which is the length of the time above which you will get slowest 15% of the trips. So slowest 15% of the trips means probability that your trip time is exceeding that small x value is equal to 0.15. 15% is written in terms of a proportion, 15 by 100, which is equal to 0.15. And you have to find out that level of time, small x say, above which it happens. So we have to use qnorm function over here. Q stands for the quantile. So one can see a qnorm command over here, which is present in help window. Qnorm syntax is same. Basically, the first parameter you need to understand is the corresponding probability that is appearing on the right hand side. So pnorm command, basically what it does is it will give you the probability. Let me write it over here. So pnorm command, sorry, qnorm command will give you the smallest value of x such that probability that capital X is greater equal x is greater equal that probability say p. So right now my probability p is 0.15 and we will be getting that small x. There is a small correction over here. It will give you the probability that capital X is less equal small x, for which that probability is greater equal your probability value 0.15. But I want the probability that the length of the time above which you will get slowest 15% of the trips. But the qnorm function will give you the probability that capital X is less than or equal to small x. It will give you that small x value for which this statement is true. So what we will do is we will convert this D part statement in the form so that we can apply qnorm command like this. So it will give you 1 minus probability. So let me write that D part statement again. So we want that time above which you will be having slowest 15% of the trip. So this is our question statement. I can write it equivalently as 1 minus probability that capital X is less equal x, which is equal to 0.15. So in other words, I want that x such that probability is less than or equal to small x is equal to 1 minus 0.15, which is equal to 0.85. So basically we want this probability that the value of small x for which the probability that capital X is less equal small x is 0.85. Now here we can use qnorm command because qnorm command works for the lower tail. So I will write qnorm of the first parameter in the syntax is your probability on RHS, whatever is given, which is 0.85, comma your mean, which is 24 minutes, and your standard deviation, which is 3.8. And this command, if you feed to R software, it will give you the answer. So that I have already written over here. So to find the length of the time above which we will find slowest 15% of the trims, you can find it using qnorm command, which is 0.85, 24, and 3.8. So if I put it in the console, answer of the x above which you will get the slowest 15% of the trips. So if I compile, we'll get the answer 27.93845 something. So above this time, so if the lawyer exceeds 27.93845 minutes, so this is the smallest value above which you will get the slowest 15% of the trips. So this is the use of Q norm command. Q stands for quantile. So you will get that quantile for which you will get the highest 85% of the trips, or in other words, slowest 15% of the trips for the complement of the event. So that is how the D part you can solve. And the last part is quite important because it's a combination of two different probabilities, namely a binomial and normal. So let us go to the last part of this question. To find the probability that two of next three trips will take at least half an hour. So total number of trips is 3. Out of that, I want 2 trips which will take at least half an hour. So my success here is if the trip takes at least half an hour, I will call it as a success. If your trips take other than half an hour, I will take it as a failure in binomial experiment. So total number of trials in the binomial experiment is 3. So basically it's a binomial probability 2 comma 3 comma p, where p stands for the probability of success. Now my success is if the trip is taking at least half an hour, I will call it as a success. And its probability we have already found in a part of the question, which is 0.0571. Using R only, we have found this a part of the. So probability that we have got in a part of this question, I will take it as a probability of success in E part. And total number of successes we want exactly equal to 2 out of 3 trials. So it is B2, 3, 0.0571 we need to calculate to get the answer for E part of the question. So once this is clear, you have to apply D binom function, which gives you a density for a binomial probability distributions for x is equal to 2, n is equal to 3, and p is equal to 0.0571. So that I have already written in the script file. To find the probability that two of next three tips will take at least half an hour, we'll use D binom function. D stand again for the density of binomial distribution 2, 3, 0.0571 is a probability for taking where the trip times are at least half an hour, which we have already calculated before. After that mice example, you can see here we have calculated it. If it takes at least half an hour, here we have to find the probability that it will take at least half an hour. This 1 minus p norm 30, 24, 30.8, and its answer was 0.0571, which I can show you in the console also. Here we can see 0.0571 was the answer. So that probability we are taking in the last part of the question, namely E part of the question. So let me just compile that command, last command, and over here, press Ctrl plus Enter, it will give you the answer. So 0.00922 something is the probability that you will get exactly 2 trips out of 3, which will take at least half an hour to reach the office by the lawyer. So this is all about D norm, P norm, and Q norm command. D stands for density, P stands for the lower tail probability calculations, Q stands for the quantile. It will give you that smallest value small x, such that probability that your random variable capital X is less equal small x will be greater equal some probability. Now the last command that is left is R norm command. So you just look at this R norm command syntax. It is n comma mean is equal to 0 and standard deviation is equal to 1. So let us use this R norm command right now, and R stands for randomness. So R norm command will generate a random set of n normal random variable values which follows a normal distribution. So suppose I say R norm 10 comma say mean is equal to 0 and standard deviation is equal to 1 only, it will give you the random set of 10 values which follows a normal distribution curve. Again, if I press the same command, suppose I run the same command, R norm 1001, it will give you again another set of 10 values, random 10 values, which follows a normal distribution. So if I again say R norm is equal to say 100, 0, 1, it will give you 100 values which follow the normal distribution curve. Their probabilities are normally distributed. These are the probability values which are normally distributed. So if you say, for example, if you have to see the nature of these probabilities, it will go through a bell-shaped curve. So the randomness is important because you can then experiment mean values and the standard deviation values of all these 100 things. Say for example, previously I have given or generated 10 values only. You can find out mean of all these 10 values that you have got using R norm function. For a second set of 10 values also you can find the mean. That mean should be nearby 0. So in a first and second command that where we have generated only 10 values which follows a normal distribution, you will get the mean value slightly differing from 0. But as you go on increasing your random values which forms a normal distribution, say for example in the third command I have generated 100 values which follows a normal distribution curve. The mean of all these 100 values, if you try to find it out, it will be nearer and nearer to 0 as you increase your value of n in R norm command. So it will become more and more normal as you increase the number of random values that you have given in R norm command. With this, we'll like to stop. If you have any question, you can write in the comment box. Thank you.